Have you two signed in yet?
Yeah.
All right. Make sure the audio's coming
You know
through.
when they're gonna lift that rule that like prohibits clubs from serving food?
Oh geez, this stream is like a half a minute behind. Interesting. Oh, no serving food? I have no idea.
Yeah.
Yeah.
He said it only when he said just mentioned it.
What, Rainbow Crack?
I think it's L-A-T-H-E-I.
I have no idea how to spell his name. Don't tell him that. I hope he's not watching the stream, but I don't know how to spell his name.
Should I look at his name too? Not really though. You can look at him if you want. No, I'm actually not looking at this for it's not actually.
Are you going to open the TD after?
Yeah.
Thanks.
I would say bad almost, but I actually.
Well, it's about time, I guess.
Yeah, it's live on audio. Oh, my laptop. That's
All right, well, if there's people watching the stream, they can sign in here, although this has been here for a while, so they probably have. All right, so this is part 2 on crypto stuff. And it's the same announcement here as before. If you haven't started the CTF that we put up, the link is right there.
Wait, there's a CTF.
Yeah, there is. It's just a good thing I had this. Did you get it? Alright, well, last time we talked about like different kinds of data encoding schemes, like how numbers are encoded, the different base systems such as binary and hexadecimal. Then we talked about ASCII, which was just how you can represent text as numerical data. And then base 64, which is, I guess you could think of it as the opposite. You can have arbitrary binary data as plain text, which is just useful if you want to have something where like you want just plain text and it can have any data. And then substitution ciphers, just like mono and polyalphabetic ciphers, such as like shift ciphers, which is like generalized form of Caesar cipher, where you just shift n letters instead of like 3. And then one-time pad, which is just like you add the key onto the plain text to get the cipher text, and it's easily doable with XOR. And also talk about modular arithmetic, which basically there's a point after which the numbers wrap around. You can either think of it as like the hands on a clock. So like 13 is 1 mod 12 because it wraps around at 12 and then goes to 1. And another way to think of it is probably what people are more used to if you're programmers, is just like remainder division, where 13 divided by 12 is 1 with a remainder of 1. And so first, my friend reminded me of this one tool, which is similar but also different from the decode.fr. It's called CyberChef. It's made by GCHQ, which, if you don't know what that is, it's basically like the British version of like CIA or whatever. And you can do interactive data manipulation, and you can also chain various operations, and it can also try to guess stuff based on just what you gave it. So it looks like this. Basically, you have a lot of different things that you can pick from. A lot. But if we see, let's see, have see. If I just punch in this input, then there's this like fancy magic wand button, which will then, it's like, oh, this is base 64. And then without this, if we hide this, you would just get a bunch of numbers, and it's like, oh, well, this is ASCII. Now, it didn't go any further from here, but if you remember, for example, shift ciphers, we can do that if we just grab the ROT13 block. They just use that one for generic, but we can then just scroll through these different values here, and then we can figure out what it is. Oh, that's way too high. But then there you found the message. The message just CSG is cool. But CyberChef is a pretty great way because you can just like play around with stuff. And if instead they have this magic button, it doesn't quite work always very well, but it'll look like this, where it'll give you a bunch of things to choose from. It's like, well, if you apply this operation, you get this, and then you can continue from there. So it's pretty neat. And then, so like the first thing that we're actually going to talk about today is hashes and hashing algorithms. So a hash is just a way that you can give some bit of data an identifier which is mostly unique. And something that hashes all have in common is that you have an arbitrary amount of input, and it gets mapped to some output which is a fixed size. And you can sort of think of it as like extremely lossy compression, but not really. We'll talk about that in a second why. And hashes are kind of random numbers as well, depending on the hash that you're using. And it's the result of a good hash is a result of a one-way function or a trapdoor function where you can only go in one direction, you can't go backwards. And certain types of hashes are good for verifying data integrity and whatnot. So hashes are not encryption. Unlike encryption, which can be decrypted, a hash can't be unhashed. There's no like reverse hash algorithm. It's also not compression, because similarly for like if you have zip and gzip or xz, which is just lossless compression, you can decompress the data, you can get exactly back what you put in. Hashes, you can't go back, but you lose a lot of data because however much data you put in always gets output as a fixed length. And it's also not really lossy compression, because if you look at stuff like JPEGs or MP3s and whatnot, it's still like, it looks similar to the original bit of data, but a hash ideally does not look similar at all to the data that went in, because that would make for a pretty bad hash if you can like look at it and be like, oh, that's pretty close to that. Then you have one type of hash is a non-cryptographic hash function, which is, it's useful for constant time data structures like hash maps, where you take some bit of data, you get a hash value, and then use the hash as an index into an array, versus like a list where you would have to iterate through everything. And non-cryptographic hashes are random enough for this purpose, but you can expect there to be collisions, sometimes a lot. One example of a non-cryptographic hash is the String.hashCode function from Java. Here you can see how it calculates a hash. It's basically the first character of the string multiplied by 31 raised to the power of the length of the string minus 1, and then it's the next character times 31 to the power of n minus 2, and so on all the way to get to the end, where it's just the ASCII value of that character. And it returns an int, which is 32 bits, so if it goes above 32 bits, well, it's going to wrap around. That's where you get like the constant size output. But if you take, for example, the string ABC, you have 65 times 31 squared plus 66 times 31 plus 67. Those are the ASCII values of the characters, and then you get 64,578 is the hash value. But if we want to work backwards from that, well, the easiest way is to just remove 131 from the second, I guess, digit, so to speak, and then just add that to the end, so that we get 65 times 31 squared plus 65 times 31 plus 67 plus 31. It's still the same 64,000 whatever, but if you convert those characters or those values into characters, you now get AAB, which is a different string but hashes to the same value. So String.hashCode is not a very good hash function if you're trying to get truly unique hashes. Now, cryptographic hash functions, they're quote-unquote true trapdoor functions, where once you do start calculating it, you can't undo it. And there are various different ways to guarantee that it's a trapdoor function. For example, you can cut pieces of the input and then just like stack it on top of itself, for example with an XOR, and then once it's stacked on top of itself, then, well, you can't unstack it anymore because all the data is together. And a cryptographic hash function is indistinguishable from random numbers. If you have a set of some n-bit random numbers and then you have n-bit hash values, no, you wouldn't be able to tell which one's the random and which one's the hash values. And if you have a small change in the input, you'll get completely different output. That's how you get like you can see pretty quickly that it looks random. And then a good cryptographic hash function, it should be impractical to find collisions, because, well, unlike the string.hash, that was pretty easy to find a collision. You just work backwards from it. But with cryptographic hash functions, you can't work backwards. So generally there's not very good methods of finding collisions. Cryptographic hash functions are useful for verifying data, and the most common use is probably passwords. Passwords are stored on your machine as a hash plus a salt. The salt is basically just an extra bit of data that is added to the input to get a unique hash. So if two people say have the same password but a different salt, they'll get this different hash as a result. And cryptographic hash functions they should be quick to compute, because if you're, for example, going through a bunch of passwords, well, you don't want that to take a long time. So nowadays, modern CPUs have hardware built in for computing stuff like SHA values, so it's pretty fast. And here are some examples of good cryptographic hash functions. It's a SHA2-256 and SHA2-512. Those are more commonly known as just SHA2-256 and SHA2-512. They superseded a previous, it was called SHA-1. It's completely broken, that hash, so these two have not been broken yet. They've only been broken in the sense that if you restrict the number of like iterations of the internal computations, you can break it, but it's, for example, like 46 rounds out of 64, so like you're not very close to breaking the actual hash. SHA-3 is a newer version of SHA-2. You have the same 256-bit and 512-bit outputs, but uses a completely different algorithm. And another one is a whirlpool hash. It's based on AES, so it uses a similar construct as the AES encryption algorithm, and it has a input size limit of 2 to the power of 256 bits. I don't think that's going to be really an issue there, and you get 512 bits of output each time. And here you can see the same ABC and AAB. These are the SHA-256 values, so they look pretty random. And it's also 256 bits, so you've got what was that? 32, I think, bytes. Let's just say 32. And then a bad cryptographic hash function is MD5. It replaced MD4, which was shown to be bad. So the guy who created it, Ron Rivest, actually one of the guys from, he's the R in RSA. So he created MD4, and then he also created MD5 to replace it. You get 128 bits of output from MD5, but the problem is collisions can be calculated fairly easily. And here, if we go, some guy wrote a neat little program. I don't have it installed, but basically here he talks a bit about what just a collision is there. And then here he has basically a program where you can feed in another program and it'll have the same hash as a second program. So the two programs are completely different, but they'll end up having the same hash. So if you just run an MD5 on there, you'd be like, oh, these are the same programs. But here, the first one is just basic hello world, and the other one is like, it'll supposedly erase your hard drive or something like that. So MD5 is not a good thing to use. The problem is MD5 is still fairly common, especially on older machines. It was the default password hash, especially on Unix machines. So if it's broken, if you can find a collision, well then you can find basically a second password for an account. And Unix does use salts, but if you can get the shadow file, then it has the salt there in plain text, so you can just apply the salt yourself. And let's see. And then now I said you can't unhash, and I guess if we assume that there's no weakness in the algorithm, so unlike MD5, then you really can't. You can brute force, which is basically just you check every single thing, and it's pretty expensive in computation time. You're checking through a lot before you might find something. Most likely you won't, especially if it's like, say, a long password. It's going to be infeasible to try to brute force that. Another option is word lists. Word lists are pretty expensive in storage space because you have to store a bunch of things to try. So instead of brute force, you just try a list of things. And it's a bit less expensive than brute force in computation time, but it's still fairly similar because instead of brute forcing over through every permutation, you're basically just brute forcing through a list of things. And then rainbow tables are another option. They're pretty expensive in storage space, but a lot less expensive in computation time because part of the storage is basically you store pre-computed values. So say you have a hash, and then you can look in the table, like, do you have this hash in the table? If so, you can just follow it up because each, I guess, entry is linked to another one, where like, if you have an entry 1, you can follow that and you'll get to what hashes to that value and so on and so forth. So if you can find your hash in the table, well then you can pretty quickly find something which hashes to that. But the problem is rainbow tables don't work for salted passwords because if you have some hash value, you might find something which hashes to that, but if you try to input that as the password, for example, then it doesn't account for the salt, so what you input hashed combined with the salt is not going to be the same hash. And there's a couple of hash cracking tools. John the Ripper is a pretty classic one. It is CPU based, and you can do brute force as well as word lists. And in addition to that, it can also do permutations on the word list, so it can change the case of the words on the fly. It can swap some symbols into there, for example, replace letters with numbers, stuff like that. So it can give you a bit more than just a basic word list. And then Hashcat is a newer password cracking tool. It's CPU, and you can also use the GPU for acceleration there. It can also do the same brute force and word lists. And then Rainbow Crack is a tool that lets you generate rainbow tables, and then you can also use the rainbow tables to try to crack passwords.
What's the difference between hash cracking, and undoing hash?
Well, undoing would mean you would be able to work backwards through the steps how to get to that hash value. But in this case, you just have the answer and you're blindly trying things until you get something that hashes the same value.
So that is by going back to how the hash was created?
Yeah, because a hash algorithm basically, once you start computing, it does various operations which are impossible to undo. As far as we know, we haven't. There's always a possibility that you might be able to break it, but as far as we know, they're not breakable. But, so basically it's like, XOR is, I guess, the easiest one to think of. If you have some number XOR some other number, and you have that answer, it's gonna be hard to find the two exact numbers that you put in, but you can obviously find a lot of different numbers that XOR to the same one, but it's pretty unlikely that you'll get the exact two numbers. So in that sense, XOR it's a good example of the concept, but it's a bad example of in practice, because you can obviously find a collision on the answer pretty easily. And then, oh yeah, here's also the links there. They're all free to download, free to play with. John the Ripper has like a premium version, but I don't know if anyone actually uses it. I don't know if you get anything fancier with it either. Alright, but RSA is an encryption scheme. It uses asymmetric keys, sometimes called public keys, where you encrypt with one key and then you decrypt with another, so that way you can have, say, Alice will encrypt something to Bob, and then only Bob can decrypt it because only Bob has a decryption key. And so, in theory, that's a good idea, but in practice, it's impractical if you want to really encrypt a lot of data, because symmetric keys like AES are much faster. Again, you have CPU hardware acceleration for AES, but public key or asymmetric schemes they're much more computationally intensive, so they're useful, for example, if you want to exchange a symmetric key, you only have to encrypt that piece of data, but then you can use something like AES to quickly stream encrypted data across. And public key encryption the security comes from the assumption that it's hard to factor large numbers into primes. So, as far as we know, there is no efficient algorithm for factoring primes. Especially as the numbers get large, there's a lot of options to try. But who knows? I mean, quantum computing eventually will be able to break RSA and all that stuff, but I believe the largest number that a quantum computer has successfully been able to factor is, I think, was it like 21 or something? So I think we're pretty safe right now. Because RSA will use something like 2048 bits, and 21 is not even close to 2048 bits long, so we're good for a while. But RSA keys you have two unique prime numbers, P and Q, which you keep them private, and then you compute a public modulus, which is just P times Q. So that's why you want to keep the primes private, because you share n with other people. That's part of the public key that you give out. And then you compute the totient function on n, which you keep private. It's basically the least common multiple of P minus 1 times Q minus 1. And then you'll choose an encryption exponent, which is between 1 and the totient of n, exclusive, somewhere in between. And one thing you have to pay attention to is the exponent and totient of n have to be co-prime, which means those two numbers may not be prime, but they're not allowed to share any factors other than 1. And then you can compute the decryption exponent, which then you also keep private. It's basically d is congruent to 1 over the exponent mod totient of n. Or in other words, d times the exponent is congruent to 1 mod n, or mod totient of n. So to encrypt with RSA, it's pretty easy. You have a plain text message m, and then you have a public key from someone, which is just the exponent and then the modulus. If you want to compute ciphertext, it's just message raised to the power of the exponent mod the modulus. What you end up with is the ciphertext. And if you want to decrypt it, then you have the ciphertext C, and then your private key is the decryption exponent and then the public modulus. And to compute the plain text, you just take the ciphertext, raise it to the decryption exponent, mod n again, and you result in the message. This shows you kind of the idea. It's not mathematically sound, but it's much easier to just get the idea, where if you have the ciphertext, which is raised to the d power, and then the ciphertext is just message raised to the e times d, and then e times d is 1, and then you end up with the message. Now it's not quite the full, I guess, reasoning behind it. The real reason is it's a bit more complex and requires more number theory than we have time for. But then here's just an example of computing an RSA key. So for example, if you have the primes 61 and 53, multiply them together, you get 32, 33 as the modulus. And if you want the totient of n, it's p minus q, which is 60, or p minus 1 and q minus 1 is 60 and 52. The least common multiple of that is 780. And then the encryption exponent has to be between 1 and 780. And in this case, let's just choose 17, because 17 and 780 are coprime. And then to compute the decryption exponent, you just have to compute the inverse of the exponent, which in this case is 413. You can check it. If you take 413, multiply it by 17 mod 780, you'll get 1. And then to encrypt it, for example, if the message is 65, which is just the ASCII value for A, then you would just take 65 raised to the 17th power, which is 2790, after you take it mod 3233. And then to decrypt it, you would take the ciphertext 2790, raise that to 413th power, take the mod 3233, and you'll end up with 65. Then there are some, just plain vanilla RSA is not completely secure. For example, if you have a really small exponent and a really large modulus, a reasonably small message raised to the exponent might be less than the modulus itself, which means, well, basically you're just raising it to the power, which means then you can just take the inverse of that, which is the eth root of the ciphertext, and you'll end up with the message. So for example, if you use an exponent of say 3, and then you have a modulus that's say 2048 bits long, and you want to, I don't know, encrypt the message, just some small blurb of text like, yo, are you coming? When you raise that to the 3rd power, it's not going to be close to the 2048-bit number, which means then someone who intercepts the message just can take the cube root of that, and then they can read your message, even though you think it's secure. And then there's a interesting thing, it's called the Chinese remainder theorem, where if you have numbers which are greater than 1, and they're pairwise coprime, which means any n1 and nk, they don't share any common factors among themselves, and then you have some integers which are non-negative, a1 through ak, then among all those there is one x which is congruent to a1 mod n1 all the way through ak mod nk. So if you want to find that x, then you can sort the different statements by decreasing moduli. So first you want to find a solution between the first two of them. So you'll try every single x1 that is congruent to a1 until you find some x1 which is then also congruent to a2 mod n2. Then to find the solution to the next one, you find an x2 which is congruent to the previous one that you found, x1 mod, but in this case you multiply the two of them together, so it's n1 times n2, until you find some value for x which is congruent to a3 mod n3, and then you repeat this until you've gone through every single statement that you want to compute. So here's just an example. So if you have 4, 3, and 0, and then you have the modulus 5, 4, and 3, you want to find the x value which is congruent to all of these individually. So first you'd start with just all the values that are congruent to 4 mod 5. So the first choice is 4, and then, well, that's 0. That's not 4, or that's not 3. So then the next one that's congruent to 4 is just you add 5, because a plus k is congruent to the a mod some number every single time. So then 4 plus 5 is 9, which is 1 mod 4. If you add 5 again, you get 14, which is 2 mod 4. 5 again, you get 19, which is 3 mod 4. So now you have number 19, which is 4 mod 5, and it's also 3 mod 4. So now you want to find a number that's also 0 mod 3. So then you'd start just 19 is 1 mod 3, and here 19 we add 20 because it's 4 times 5. You multiply these previous ones together. So 19 plus 20 is 39, and that's 0 mod 3. And if you want to verify that that actually works, then 39 is 7 times 5 plus 4, and then 9 times 4 plus 3, and then 13 times 3 plus 0. So these are your remainders here, and they match up with that. Then with RSA, you can use that to your advantage a bit. If, for example, you have the same message and it's encrypted n times, and then that n matches up with the public exponent, but each message is encrypted with a different key, so P and Q are going to be different, but the modulus is the same that's used in the key. Then, well, you can see a similar statement here where some message raised to the exponent is your first ciphertext mod n1. You can start seeing a similar pattern here. So from here you can then find some new value that is also then congruent to all of those. Let's see. Let's see. I think CyberChef actually has some RSA stuff. Let's see. Public key. RSA. So I guess if we clear this. Do we have to give it? I hope we don't have to give it a key. Oh, shucks. We do have to give it a key. We generate a key. That's a PGP key. Oh, there we go, right here. Then, I wonder how we can give that. Well, here we go. Right, public key. What? Oh. Okay then. Message is too long. Well, there we go. Where's the... But base 64, for example. X. Yeah. But for example, if you want to encrypt stuff, then you can just punch in your text here. It's pretty interesting. I think CyberChef has. You can download it.
Yeah, no.
It probably works a bit better than on the browser because the browser is limited in performance. I'd imagine, especially if you have like try to do any of the automated stuff, I'd imagine that probably would work better on the browser. Well, you can do all the same stuff, I believe. I've actually never tried to download it. Is there any like different stuff?
I haven't even unzipped it yet. I just did it so I don't forget.
Alright. But you can do all sorts of stuff.
So
Encode the text.
You can kind of like, oh, I see, you're kind of like putting different
Yeah,
blocks together almost.
yeah, there's a generate RSA key block, and then from there we got the public key and I copied that into here, and then just output that as hex. You could do the same thing in reverse if we RSA doesn't have a salt, but if we go, there is a somewhere here. No. Do we have? Decrypt. Wait, there's a search. Why am I not searching? Oh, it doesn't let us it doesn't let us choose a salt. That's a shame. But here you can also then choose how many rounds you want to do. If you only did 33 rounds, that would be broken because that's way below the value that they had broken SHA2-512 for. But I think the standard is 64 or something. Let's see what else is. I want to see if there's one that has a salt. No, I don't have to. I actually have a program that does that. Let's see, 18. I think that's large enough, right? Where is that? Do I have that here somewhere? I should. But here, we can give it a password, for example, ABC, give it a salt value of just like 1, 2, 3, and you'll this is a perfectly valid hash value they can then punch into etc shadow. I basically created this little program because I need to fix my etc shadow at one point. So this was the easiest way to generate them, but if we give it a different salt, it's a completely different result there as the hash. And the John the Ripper and stuff like that, they'll, for example, they'll accept this format and they'll pull out the different salt value. In this case, 1, 2, 3, and here it's 1, 2, 3, 1. The number 6 there, it basically means, I think it's SHA2-256 or SHA2-512, I don't remember exactly. But it gives the algorithm, and then the rest of this is just the hash. I believe it's base 64, but slightly modified base 64. For example, there's dots in there. Let's see. We just it doesn't actually tell me which one I used. SHA2-512, that's number 6. But I think that was the last slide, yeah. Any questions? About anything? Pick a slide. Do you have any questions about anything? Have you had to break any hashes on your exams?
I did break there was one in an exercise for labs, but I didn't go that route in the exam. It was the Ansible route hash. But I can't remember what type is it, but I know HashCat has them.
HashCat can support a lot of stuff, just like John the Ripper.
Yeah.
If the hash algorithm exists, it might support it.
Yeah. But I think, let me try.
Another neat thing about John the Ripper is like, you can people have written like plugins and stuff. So if you want to crack a format that it doesn't understand, then you can convert it to something it does understand.
Yeah. So,
I'll show you this. Ansible volts. Code number is 16900. So
Has anyone tried this program yet? Has anyone tried the MD5 program yet?
Oh, I've seen that. I've actually read it a lot.
Right. Have you tried the program?
No, I haven't. I think it was a little tricky. I don't know. I forgot how to do it. I didn't do it though. I just read about it. Just something that I don't understand. So.
Come on, it's simple English.
I mean, no. I understand. I can read. I'm not saying I can't read. I can read, but I just don't grasp the concepts. Like I wanted to get into cryptography for a little bit, just to understand, like at least how the algorithms work for a lot of the encryption protocols. I always had a hard time. I know how RSA works.
Shatter, that's the one.
Kind of,
You can take Desmond.
This was the.
You can take Desmond.
What's that?
You can take Desmond's crypto class.
Oh yeah, Evo Desmet. But you'd probably want to have a solid base in number theory.
Yeah. Well,
Oh yeah, here's
such a
Google broke SHA-1 back in 2017.
Yeah. Nothing wrong.
It took 20 years, but they did it. So if you ever see anyone using SHA-1, you can tut at them and be like, no.
How does a collision lead to an exploit?
Well, now you have, if you can compute the collision, for example, a password hash, you can basically compute a new password.
Yeah.
And you can also then, if you use it to, like what this program here is, is hashing two programs to check, oh, well, I want to make sure I'm running the program that I downloaded. Download the MD5 hash. If you just hash it, you won't know if you downloaded hello.exe or erase.exe, because they both hash the same value.
Yeah.
So if you can compute a collision, kaput. The entire algorithm's broken. And there are
I see why it's broken, but, like,
there are different ways also you can break stuff. Is like, you can either, if you have the hash, you can compute some other input that hashes to that. Another way that you can show the algorithm is broken, if you just compute two collisions in general, to where it's like you just compute two things which hash to the same value, instead of like going backwards where you find something which hashes to a specific value. You just want to find two things that hash to the same thing. That's another way to break it. Arguably, I'd say being able to compute an arbitrary input for a hash is more powerful than just being able to get two arbitrary inputs that hash the same value. But
yeah.
It's not like a perfect example. It's not like but it's
is there anything else? Anyone have any other questions? Boom. Everyone's favorite screen.